everybody, I'm going to talk about reactions of alcohols with acid in this video. So the thing that I want us all to remember when we're talking about alcohol reactions is that many of them are still just based in substitution and elimination. Okay, so we're going to look at that pretty strongly in this video when we're thinking about if I've got an acid, what's going to be the mechanism, what is going to be, is it substitution or elimination that's going to be the major product? So this is kind of how I like to break it down in my head. We're really thinking about an option between, I can either have a nucleophilic conjugate base, okay, so where X is going to equal chlorine, bromine, iodine, so things like hydrochloric acid, hydrobromic acid, hydroiodic acid, those are going to be our nucleophilic conjugate bases, because once we protonate and we end up with that Cl minus, that Br minus, that I minus, those are going to be good nucleophiles. They're really bad bases, but they are good nucleophiles. So we can either have a situation where we're using an acid that has a nucleophile associated with it, or if we use something like sulfuric acid, okay, so let's just kind of make a little note over here, Cl minus, Br minus, I minus, those are all good nucleophiles. But over here, if we've got HSO4, this is a bad nucleophile. Okay, so we're looking at either having good nucleophiles around after we do an acid-base reaction or having a bad nucleophile around. Okay, so if I do have a good nucleophile, we're looking at some kind of substitution. Is going to be our major product. Okay, you've got a nucleophile, it's going to substitute. If I don't have a good nucleophile, we're going to eliminate. Okay, and we're going to look at examples of both of these. But then once we get to deciding whether we're having a substitution or an elimination product, we need to be thinking about what kind of substrate are we working with, because that's going to dictate what kind of mechanism we're going through. Okay, so basically, if you have an alcohol that is set up to give you a good carbocation after your alcohol leaves, namely a secondary or tertiary alcohol to give you a secondary or tertiary carbocation, it's going to go by the SN1 route. Okay. However, if you've got a primary alcohol, because now you're looking at something that's going to be a very poor carbocation, it's going to go faster just to have it go through an SN2 type mechanism. Okay. And keeping in mind that all of the same little nitty-gritty rules that we've gone through in terms of thinking about carbocation rearrangements, thinking about inversion of stereochemistry, racemization of stereochemistry, those are all still present in these categories when we're looking at alcohols and acids. Okay. On the other hand, if we're looking at the elimination, we essentially have a very similar setup where those secondary and tertiary alcohols are going to give us that E1, give us that stable carbocation to go by an E1 mechanism, or a primary alcohol, which would not make a very good carbocation, is going to go more E2. Okay. So let's take a look at a couple of examples so that we can see how this all boils down. Okay. So the very first thing that I kind of want you to think about is just the reaction that we're looking at here. Is something like this. Okay. And the primary alcohol is kind of a finicky one. So X is going to be bromine and iodine, not chlorine. The chlorine is actually not a strong enough nucleophile for this particular reaction when it's on a primary alcohol. Okay, so we're looking at putting an alcohol in with this acid, and then we're going to get out, in this case, since we're using a good nucleophile, we're going to get a substitution reaction. Okay, so we're going to substitute the OH for the halogen. Okay, so it's another way of making alkyl halides. So the mechanism here, because we've got a primary alcohol, it's going to go by SN2, I guess I should say primary alcohol and nucleophilic conjugate base. All that together is going to give us SN2. Okay, so our mechanism here is we can't just go, I'm going to change this to a BR so that we're doing something specific. I can't just have the HBr go and attack and move over. Okay, couple things wrong with that. The first thing, this bromine is not yet a good nucleophile. Okay, it is not in a nucleophilic state at this point. It does not want to have a proton and be attached to a carbon. That's not going to happen. The other problem with that is that this OH is a really bad leaving group, particularly in highly acidic conditions. Because basically you're trying to say, get out you base, like strong base, right? OH minus is a strong base. You're trying to kick a base out into a highly acidic solution. That's not going to happen. Okay, the very first thing that's going to occur here is we're going to have our OH get protonated, and we're going to do an acid-base reaction first. So we're going to protonate the OH to make it a good leaving group. And we're going to generate our nucleophile. Okay, so now I've got a good leaving group here. And that good leaving group is going to now be able to make space for our nucleophile in an SN2 reaction. Okay, to get our products. All right. So if we have a situation where we have a different type of alcohol, so this was an instance of a primary alcohol. So let's look at a tertiary alcohol. Okay, so for a tertiary alcohol, in this situation, we can use chloride. Okay, so we can use hydrochloric acid as well. We're going to substitute that in for our OH. Okay, so if we look at the mechanism here, since we've got a tertiary alcohol and we've got a nucleophilic conjugate base, that's going to give us an SN1 type mechanism. So for SN1, we're going to do it with HCl this time. So in this situation, I still am in a position where the OH is not just going to come off as OH minus. Okay, we've still got a bad leaving group here. Okay, so our first step, whenever we've got a strong acid, we're still going to protonate that alcohol. Okay, protonation is the easiest way to turn an alcohol into a good leaving group. Okay, once it's positively charged, now we've got a good leaving group. And now we can go through an SN1 mechanism and just have that pop off. Okay, since we have drawn a carbocation, we always want to be looking for rearrangements. In this case, I've got a tertiary carbocation. My other options are worse, so we're not going to have one, but we want to think about it just in case. And forgot to put in my chloride back here. Okay, that's still just kind of kicking around, and now it's ready to act as our nucleophile. Okay, and again, we'll end up with racemization of that stereocenter if it was a stereocenter. In this case, since it is not a stereocenter, I don't have anything to worry about. Okay, so that's going to be this side of this little flowchart thing. Okay, so we're looking at anything like HCl, HBr, HI. Those are all going to give us substitution, and then you look at what kind of alcohol you have to determine whether or not it's going to be an SN1 mechanism or an SN2 mechanism. Okay, so let's look at the H2SO4 for a little bit here. So let's start off with a primary alcohol. Okay, the thing that we want to note here H2SO4 can't really occur without some water present, even when it's concentrated. Okay, so when we're talking about concentrated sulfuric acid, it's a guarantee that you're going to have some water. So we're really looking at this acid-base reaction here, where we're looking at the acid-base reaction of sulfuric acid and water, and that's going to dissociate to be HSO4 minus plus H3O plus. And then this is going to be what most of your acid-base chemistry is coming from. Okay, so when we're looking at that, we're really looking at H3O plus as kind of being our proton carrier. Okay, so if we're looking at this one, I've got a primary alcohol. I've got a non-nucleophilic conjugate base. Okay, because keep in mind that my water and my sulfuric acid is highly skewed to the product side because of how acidic sulfuric acid is. So this is a bad nucleophile, and H3O plus is also a bad nucleophile. So that's mostly what we have around. Okay, we're going to see tiny little bits of water that we're going to use in our reaction, but just to make more H3O plus. Alrighty, so we've got primary alcohol, non-nucleophilic conjugate base. That's going to give us an elimination, and because it's primary, we're not going to form a carbocation, we're going to go E2, okay? So that means we're going to end up getting this product out, and let's take a look at the mechanism here. Okay, so I'm going to use H3O plus as my little proton shuttle. First thing, I'm always going to protonate. Okay, pretty much all of these alcohol with acid reactions, the first thing you should do is protonate and then think about what you need to do after that. Okay, so now I've got a good leaving group. Okay, and now I'm ready to do my elimination. So this is my alpha position, my beta position, and since I'm doing E2, I still need to do the same kind of anti-periplanar situation here. I'm not worrying about that too terribly much, just because I've got that's on a primary position, so it doesn't matter how I rotate it. But if you are in a situation where it matters, just consider like you do need to think about anti-periplanar, but it usually doesn't come up that much because you're only dealing with primary positions. Okay, so this is where we're going to use our little bits of water. Okay, so we're going to use a little bit of water here to go grab that proton, eliminate the proton, kick off our leaving group, and then we get to our final product, okay? And then along the way, we made more H3O+, okay? So you're still kind of feeding into this whole acid-base reaction on the side. All right, so let's look at what we get when we do it with a secondary or tertiary alcohol. So let's do this same substrate. We're going to throw the concentrated sulfuric acid in. Okay, so in this case, I've got a tertiary alcohol, our non-nucleophilic conjugate base. So all that together is going to be an E1 type mechanism. So first step is always going to be protonation. Okay, and it doesn't matter what mechanism you're looking at, the protonation is always going to be the first. Okay, and now we're ready to form our carbocation, so we can have the leaving group leave. And now I've got a nice stable carbocation. I look for any rearrangements possible. In this case, again, there's no rearrangement because I've got a tertiary carbocation already, just secondary options on the other sides, or primary, all are worse. So now, since I don't have any nucleophile, we're looking at our beta positions. Okay, so I've got my alpha here, beta, beta, beta. Okay, and at this point, we're going to use water as our base again. We don't really have anything else that could act as a base. We're going to protonate or deprotonate, sorry, form pi bonds. So we're going to get that product, or we can have water grabbing this proton to make that product. Okay, this is going to go by the same kind of elimination rules where the more stable more substituted alkene is major. Okay, so we're looking at this as being our major product and then the other one being our minor product. But the thing that I want you to think about here, so we got these two products, is that essentially this is the only way to really get E1 as a major product. Okay, so we talked about how when you do SN1 and E1 together, SN1 tends to be the one that kind of tends to be the major product. This is going to be a surefire way of getting E1 to be your major mechanism and major product. Okay. Without any of those substitution issues. Okay, and it's all due to the fact that we're using an acid that is a really poor nucleophile, and the water is really the only thing that could be a nucleophile, but if it did act as a nucleophile, you're just going to go right back to your starting material. So it's just going to be able to keep on reacting, okay? And pretty much once you get to here, it's going to be, you're going into a little bit of a well there in terms of going to a lower energy product. Alrighty. So as always, let me know if you have any questions, and I will see you all later.